Hello everyone. Today class we are going to discuss about lanthanides and actinides, and this is the most important topic for competitive exam, and most of the MCQ questions can be asked for SET examinations also. And here today I am going to focus majorly how to write electronic configuration for lanthanides and actinides in a simple manner. And by electron configuration we will be knowing about number of electrons. Automatically we can predict the color and magnetic properties. First I am going to discuss about electronic configuration of F block elements. So students, we used to call F block elements also as inner transition elements. F block elements means the both lanthanides and actinides together we are calling it as F block elements. Why we are calling F block? Why? Because in both lanthanides and actinides the outermost electron is going to enter into the F subshell. That is the reason we are calling F block elements. And also we are calling it as inner transition elements. So here if you notice the periodic table, here you can notice. So that both lanthanides and actinides are present between the 6th and 7th period, and also it was present between the metallic and non-metals. So that's why it is called as inner transition elements. We are not writing along with the transition because where F electrons will be present, that's why we are writing in a separate series. Where 4F electrons started, that's why we are calling 4F series, and 5F electrons started, there we are calling it as 5F series, that is actinides, 4F series, that is lanthanides. So the general electronic configuration of F block elements is N-2, F1 to 14 and N-1, D0 to 1 and Ns2, where N is the principal quantum number. So here this is depending upon the period number. For example, in the case of lanthanides we can notice the lanthanides are corresponds to the 6th period, that's why we can substitute N as 6, and actinides are corresponds to the 7th period. So we can write the principal quantum number, that is 7. So if I am writing N as 6, that is lanthanide, and if I am writing N as 7, that is a. If we are substituting N as 6, that means the general electronic configuration we can write it as 4F1 to 14 and 5D0 to 1, 6S2. This is the lanthanide general electronic configuration. And if we are substituting N as 7, that means N-2, 7-2, that is 5F1 to 14 and 6D 0 to 1, 7s2. This is a general electronic configuration for actinides. So here I am showing you the lanthanides elements, the total 14 elements starting from lanthanum to lutetium. You can notice that is lanthanum starting from the atomic number 57 and cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium and lutetium. So as I said, the lanthanides general electronic configuration is this one, 4F, 5D, 6s2. This is the common for all. So I am writing the 4F, 5D and 6s2 is common for all. You can notice the 6s2 is common for all, and the only change is happening between 4F and 5D. Just try to remember students, just you have to skip the number 2 and 8. Why we are skipping those two numbers? If we are observing the splitting pattern of F subshell, so there is a greater distortion chance in when it is 2 electrons and when it is present in 8 electrons. And also it is trying to get rather than 8 electrons, 7 electrons, because the exactly half field configuration is always used to get high stability. So that is the reason we are going to skip those numbers and we are writing continuous as it is, starting from 0, 1, skipping 2, 3, 4, 5, 6, 7, and again we are writing as 7 because that is the most stable because of exactly half field, and again coming to 9, 10, 11, 12, 13. Again we are writing here 2 times 14. As we know that the 13 configuration is just before to this. If it is becoming 14, then it will become completely filled. So rather than filling electron in the d orbital, so it tries to enter into the f orbital in the case of ytterbium. So the exceptional configurations you will notice in the case of ytterbium and as well as in the case of europium. These two elements shows exceptional configurations. So once we fix the number of F electrons, we can easily predict the number of D electrons. See here carefully. So the cerium atomic number is 58. As we know, the xenon atomic number is 54. So 54 plus 1, 55, and 56, 57. How many electrons left? Only 1 electron. So that I am going to fill in the D level. Similar way, you can fill for any element. For example, coming to the dysprosium. So for the dysprosium, this is a 54 plus 10, 64. And it is 2, that is 66. So the atomic number also is 66. So there is no D electron in the dysprosium. Coming to the gadolinium. Gadolinium, this is 54 plus 7, 61 plus 2, that is 63. There is only 1 electron present in the D level. So in this way, we are going to. So we can notice here only the cerium and as well as the gadolinium and lutetium elements only having 1 D electrons. Apart from that, the all other elements doesn't have any D electrons. So from these you can say to get the exactly half filled and completely filled configuration, during this process the electron is trying to enter into the D level as because it's already acquires the stable configuration. So once we know electronic configuration of these lanthanide elements, we can easily say which is the stable oxidation state, and also we could say which will act as a better oxidant and which will act as a better reductant. And we could say if suppose the number of unpaired electrons are same, then automatically the magnetic momentum value also same, and as well as the color also will become same. So we are going to solve few of the questions regarding this topic. Few of the previous year set solved questions we are going to solve regarding this electronic configuration, particularly one by one. Students, see here, this was the first question. This was asked in the set examination. The correct electronic configuration and spin-only magnetic momentum of gadolinium plus 3 are. So they are asking electronic configuration. We know that gadolinium has exceptional configuration. That is this one. So the gadolinium is 64 atomic number and xenon 54. And we know 6s2 is fixed. That means 56s2 and 4f7 is fixed. So automatically it is having 1 D orbital electron. So the gadolinium configuration, we know that 4f7, 5d1, 6s2. As we know, the exactly half filled is more stable. It is not easy to remove electron from F subshell. So we could easily remove the 5d and 6s2. That means it can easily show the oxidation state plus 3. Why? Because you can easily remove 6s2 and 5d1, total 3 electrons. So gadolinium used to exist in the plus 3, that is the most stable oxidation state. In the plus 3 oxidation state, it is having how many unpaired electrons total? 7. Because F subcell can accommodate maximum 14. So exactly half filled is 7. So that means the number of unpaired electrons n equals to 7. The question is what? The question is, what is electronic configuration? What is the spin-only magnetic momentum? The spin-only magnetic momentum mu s can be calculated by using formula, that is square root of n into n plus 2. Where n equals to 7, if you substitute 7 into 7 plus 2, that will become root 63. The value will become as 7.9 Bohr magneton. So we know the 4f7 is fixed, this is wrong, and this is also wrong. 5f means that is actinide, but we are discussing lanthanide element. And this is 4f7, but the magnetic momentum is little higher, because root 63 value is only 7.9 Bohr magneton. So the correct option is A. Next question is, the pair of lanthanides with the highest third ionization energy is. So which of the lanthanides are having third ionization energy? So the ionization energy, third ionization energy means they are asking about IP3 value. That is IP3 value. So that means we are going to remove the third electron. So we could know that configuration first, uranium, gadolinium. So the europium configuration is 4f7, 5d0, 6s2. So you can remove easily 2 electrons. We can't remove the third electron. Why? Because it is exactly half filled. It is not easy to remove from electron from exactly half-filled configuration. So from europium, it is very tough to remove third electron. So this is correct. Coming to the gadolinium. So gadolinium, you could see the configuration here, 5d1, 6s2. You can easily remove the third electron. So this is the wrong option. Coming to this one, europium is the right. Coming to, we are going to check ytterbium. So the ytterbium configuration 4f14 and 6s2. As I said, the exactly half filled and completely filled is very stable. So we could not remove the third electron from completely filled configuration. So in the case of ytterbium also, it is very required high amount of energy to remove third electron from 4f level. So the correct option is europium and ytterbium, because those two elements used to exist in +2 state rather than +3. The lanthanide elements, all the elements if you notice, all used to exist in the +3 state, which is very stable for the common oxidation state for lanthanides, except europium and ytterbium. Only these two elements used to exist in +2 state. The europium is exactly half filled and ytterbium is completely filled. So this was the question they have asked in the set examinations and gate examination also. A comparison of the valency electron configuration of the element samarium and europium suggests that. So we should know what is the configuration of samarium and europium. So you could see here, this is the samarium configuration 4f6 6s2, and this is the europium configuration 4f7 6s2. So coming to the first option, samarium is a better 1 electron reductant than europium. Reductant means what? Reductant means the one which is undergoing oxidation and thus will act as that is helping for the reduction of other substance. So samarium used to exist normally, common oxidation state +3. So further, if it is showing +2 state, it can easily, this can show +2 and as well as +3 also. That means it can undergo oxidation. It is undergoing oxidation means it can act as a reductant. So samarium is a better 1 electron reductant. That means it is helping for the reduction of other substance that itself undergoing oxidation than europium. Next coming, samarium is a better 1 electron oxidant